Today we're going to be learning about independent samples t-tests, their assumptions, the formula we use to calculate the t-test, and then we're actually going to do some examples. So let's get started. We'll start with a little bit of review and reteach from the past 2 weeks. So our assumptions for a one sample t-test, we have that the dependent variable is continuous. We have that the sample is independent from the population, so if someone is in the sample, they should not also be in the population. And then normality, where we assume that the dependent variable is normally distributed. And we believe that this assumption is met if we have a large enough sample. So in a one sample t-test, we are comparing a sample to a population, and we do not know the population standard deviation. So in SPSS, we get an output that looks similar to the one on the right-hand side. So at the top, we'll have our descriptive statistics. And then in the second table, we're going to have the actual calculations of the one sample t-test. So we can see that the t-value is negative 4.734 with 9 degrees of freedom, which means that our sample size was 10 because the degrees of freedom in a one sample t-test is your sample size minus 1. And then we can see that our significance value, or our p-value, is 0.001. And we want to remember that if our p-value is less than alpha, we reject the null hypothesis and conclude that there is a statistically significant difference. So in this one, we can see that our test value, which is our population mean, was 46, and we're comparing that to the mean of our sample of 32. And then we had the independent samples t-test. An independent samples t-test is where we're comparing two independent samples. So men's enjoyment of a TV show versus women's enjoyment of a TV show. This has 5 assumptions. We again assume the dependent variable is continuous. We have that the dependent variable, or the grouping variable, is categorical and dichotomous. We again have normality. We have homogeneity of variance this time, and homogeneity of variance is the assumption that the variance of the two samples is not statistically different, and we use the Levene's test to calculate this. And then again, we have independence, and this is where the two samples are independent of each other. So our independent samples t-test formula is the mean of group 1 minus the mean of sample 2 divided by the standard error of the difference between the means. Our formula is mean of sample 1 minus mean of sample 2 divided by the standard error of the difference of the means. We use SPSS to calculate this as well. At the top, again, we have our descriptive statistics. However, this time we have a line for each of our two samples. So for this example, we have the no music, or the control group, and the classical music, or the. So we can see here we have the independent samples t-test output from SPSS. At the top, again, we have our descriptive statistics. However, this time it's going to give us descriptive statistics for each of our two groups, including our size, sample size, mean, standard deviation, and standard error of the mean. And then at the bottom, we have our calculations for our actual t-test. So the first two columns give us our Levene's test. Again, we want our significance value to be greater than alpha for the Levene's test, which would indicate that there are no significant differences in the variance. So we would use the top row, which we did here. We can see our t-value is negative 0.817 with 16 degrees of freedom. This means that our sample size was 18 total, because a degree of freedom in an independent samples t-test is N1 plus N2 minus 2. And then our significance value is 0.426. So because our significance value is greater than alpha, we fail to reject the null hypothesis and conclude there is not a statistically significant difference between the means of our two samples. Now for the new content. We're going to be looking at dependent sample t-tests. So a dependent samples t-test is also called a paired, matched, related, or correlated samples t-test. And the purpose is to compare the means of two related samples on a given variable. So related means the scores in one sample are somehow connected or related to the scores in the other sample. In the case of a paired sample, there's only one group. So you're looking at someone's pre-test and post-test, so it's the same person. And our variables in a dependent samples t-test, again, we have our independent variable, which is our grouping variable. It's nominal or categorical in 2 levels. And our dependent variable, again, is continuous. So an example of a dependent samples t-test would be you want to see if people's depression levels after therapy are significantly different from their levels before therapy. So this would be a pre and post paired samples t-test. So much like the independent samples t-test, we are still interested in determining whether there is a difference in the means that we observe in some samples on some variable, if that represents a true difference in the populations from which those samples were selected. However, this time we're selecting matched samples. So what is a matched sample? It could be a single person, their pre and their post test. So you can see in our lovely little photo, we have this weird bean thing who had a 47 before and then had a 46. The B had a 92 and then a 100. The monster thingy had a 77 and then an 89, and the N had a 69 and then a 68. Okay, so the variable 1 would be our pre-test score, and the variable 2 would be our post-test score. Or we could be looking at a single person over time. So math achievement from one year to the next, we might be interested in seeing if a student's 10th grade score on their state standardized test is significantly different from their 11th grade score on the math standardized test. Another example of a dependent samples t-test could be twin studies, where you're matching the twins together, or maybe a father-daughter study, or any type of family members research. You're comparing two siblings, or a mother-daughter, or a grandmother and their cousin, anything where you have some type of relationship between each of the two, between the participants. So why does it matter? Why wouldn't we just run a independent samples t-test and say that sample 1 is the pretest and sample 2 is the post-test? Well, there's a very specific reason, and it's that the best predictor of future performance is past performance. Okay, so if I had a really, really, really good score in math on my pre-test, it's very likely that I would probably get a really, really good score on my post-test. Where Jane, who's sitting next to me, maybe she's not so good at math and she didn't do so well on her pre-test. Well, she might do really well on her post-test, but knowing that before we even taught the material, she wasn't very good at that will give us an indicator that maybe she's going to improve, but not to the level that I would have. Okay, so the best predictor of future performance is past performance. So the equation for the dependent samples t-test is the observed differences between the first and the second mean divided by the standard error of the differences between the two dependent sample means. Okay, so we use these. X is the first variable, so the mean of the first test or the person 1, so the pre-test or twin A, and Y is the mean of the second variable, so the post-test or twin B, divided by the standard error of the difference between the two dependent sample means. There is a formula to get the standard error of the difference between the two dependent sample means, and it is simply this one here. It is going to be the standard deviation of the difference between the dependent sample means divided by the square root of the number of pairs of scores. Okay. Again, there is an even more in-depth formula that gets you the standard deviation of the difference between the dependent sample means. We're not going to cover that in this class though, okay? So you do need to know that if you have the standard deviation for the differences between the dependent sample means and the sample size, you can calculate the standard error of the difference between the sample means. So statistical significance in dependent samples. So we must take into account sample size via the degrees of freedom because the shape of the t-distribution changes as the sample size change, right? So our degrees of freedom is going to be the number of pairs minus 1 or n minus 1. That's our degrees of freedom for the dependent samples t-test. So what is the probability of getting a t-value of that size by chance? If the observed t-value exceeds the critical t-value, the result is considered statistically significant, and the researcher rejects the null hypothesis and concludes that there is a significant difference between the sample means that represents a genuine difference between the population means. Okay, So in the same way, if the p-value is less than alpha of 0.05, we reject the null hypothesis. Okay, the same thing as always. If your t observed is bigger than your t crit, meaning it falls in the region of rejection, you're going to reject the null hypothesis. If p is lower than alpha of 0.05, you again reject the null hypothesis. So what we're trying to say is, do the sample means, are they different enough to represent a true difference in the population means? Because again, we're always using our sample to generate information about a population. So let's do an example. Suppose I wanted to see whether students' achievement as measured by an average achievement score changed from 5th to 6th grade. I collect data from 689 students and compare their average achievement score in 5th grade to their average achievement score in 6th grade. So the mean average achievement for 5th grade is 8.08, or 6th grade is 7.3487, and the standard error of the difference is 0.0893. With an alpha of 0.05, I want to know, is there a statistically significant difference between the average 5th grade and 6th grade achievement score? Use the 5-step hypothesis test and also identify the independent and dependent variables. So I just copied over the information on the top right-hand side from the previous screen. So our independent variable is going to be their grade level. This is going to tell me if they're in 5th grade or they're in 6th grade. The dependent variable, remember it needs to be continuous, is going to be the average achievement score. We have an alpha of 0.05. Our sample size is going to be the number of pairs minus 1. So we had 689 students, so our degrees of freedom is 688. The null hypothesis. The mean of X, the population mean of X is the same as the population mean of Y. And we're using these samples to represent that population mean. So students' average achievement score will not differ between 5th and 6th grade. And alternatively, the population mean of X of 5th grade is not the same as the population mean of 6th grade, and there is a difference in the average achievement score for students between 5th and 6th grade. Is it a one-tailed or a two-tailed test? Well, we didn't say that 6th grade was going to be better or worse than the 5th grade average achievement score, so it's going to be a two-tailed. We're just interested in seeing if there is a difference, not what type of difference. And we want to set the criterion for rejection. So we're going to look in Appendix B, and we're going to look at alpha. All right, so here's Appendix B, and we know it's a two-tailed test at 0.05, and our degrees of freedom was 688, while our appendix does not go past 120 because after 120, the t distribution resembles the normal distribution, the z distribution. So we're going to use the infinity row, which means anything greater than 120. So we can see that our t critical value is 1.960. So over here, we're going to calculate the test statistic. We're going to use our formula of the mean of time 1 minus the mean of time 2 divided by the standard error of the difference between the dependent sample means. So we're going to plug that in to be 8.08 minus 7.3487 divided by 0.0893, which gives us a t-value of 8.19. We can see in our graph that the t-value of 8.19 does fall within the region of rejection. So we're going to compare the t-crit to the t-observed, and we're going to reject the null hypothesis and conclude that there is a statistically significant difference in the average achievement score from 5th to 6th grade. Okay, let's do one more. Suppose Dr. Smith wanted to assess whether her new therapy for treating depression was effective in improving clients' general mood after 6 weeks of her new therapy. She randomly picked 9 of her clients who have depression and gave them a standardized mood questionnaire. Low scores imply poor mood, or depression. Then, over the next 6 weeks, each client received her new therapy program for treating depression. On week 7, she gave the clients the mood questionnaire again. Using the data below on the pre-test and post-test scores, determine if the therapy was effective in improving mood or depression. Use the 5-step hypothesis test, also identify the dependent and independent variables, and set the alpha at 0.05. Okay, so here are the data for our example, and I have already calculated the means, and the standard deviation for you. Okay, so our independent variable is going to be the pre or the post test. So this is the type of test, whether it's a pre or a post. And our dependent variable is the score on the mood questionnaire. So each person is going to have a score from before therapy started, the pretest, and a score on the mood questionnaire again for their post-test. There are 9 participants in the clinical trial. And so our degrees of freedom is the number of pairs. Each person has a paired pre and post test. So that's 9 minus 1. So our degrees of freedom is 8. We're going to set the null hypothesis, and it's going to indicate that the mean of the pretest, the population's pretest, is the same as the mean of the population's post-test. And again, we're using our samples to estimate our population parameters. So let's write this in words. There is no difference in depression after receiving the new treatment. And alternatively, we wanted to know whether her therapy improved mood, okay? So we want to know if the population mean of the pretest is going to be less than the population mean of the post-test. Okay, so this is a one-tailed test, so it does have a directional arrow here. And the new treatment is effective in improving depression levels. Again, we did decide that this is a one-tailed test. Okay, so the first thing we're going to need to do is set the criterion for rejection. So we have an alpha of 0.05 and 8 degrees of freedom, so we need to go to Appendix B. This is a one-tailed test, so we're going to use the row for one-tailed at an alpha of 0.05, and we're going to go down to degrees of freedom of 8, so we can see that our critical t-value is 1.860. So now we need to calculate the standard error of the differences between the dependent sample means, because currently we only have the standard deviation of the difference between the dependent sample means. So we'll pull our formula, and we can see that we're going to plug our numbers in. 3.5 is our standard deviation of the difference between the dependent sample means, divided by the square root of 9 is 1.16667. So now we'll need to calculate the test statistics. So we will take the pretest score of 3.33333 minus the post-test of 7.000 divided by the standard error of the difference between the paired sample means. So you just plug your numbers in and calculate it, and you'll end up with a t of negative 3.14. Then we're going to make a decision. So we need to compare our t observed of negative 3.14 to the t critical value of 1.860. So we know that 3.14 falls within the region of rejection, so we're going to reject the null hypothesis and conclude there is a statistically significant difference in the client's general mood after 6 weeks of Dr. Smith's therapy. So now we'll calculate this in SPSS and then report it in APA.